Today, I will consider the third problem related to the statistical inference. Earlier, we have discussed the problem of point estimation, in which we specify a value for the unknown parameter of the population. Another one in the previous lecture I have introduced, that is called the problem of interval estimation, where in place of giving a single value, we give an interval for the specified parameter. The other type of problem of inference occurs when we want to test whether our parameter value satisfies certain condition. For example, if we are considering the cure rate using a certain medicine, then how many patients get cured? Suppose there is a medicine which we have been using, and it is known that approximately 60% of the patients get cured for that. So, if we use the parameter p to denote the success rate or the probability of getting cured using the medicine, now a new medicine is introduced in the market. So, here it is given that p is equal to 0.6 for say medicine A. Now, a new medicine B is introduced and the success rate with this is say p. Then we want to know whether p is greater than 0.6 or p is less than or equal to 0.6. Certainly, this is a problem of interest to the drug manufacturer and the person who is going to market it. Now, here the problem of inference is based on certain assumption about the probability distribution, because if we consider say n patients to which the medicine has been given and x is the number of successful cures, then we can say that x follows binomial n p, and then we want to test the hypothesis whether p is greater than 0.6 or p is less than or equal to 0.6 or say p is equal to 0.7 or p is 0.5, etcetera. We can make any statement of this nature. This is called a hypothesis. Okay. Now, there can be several, I have written several statements here, p is equal to 0.7, p is equal to 0.5, p is greater than 0.6, p is less than or equal to 0.6. We classify these hypotheses into different forms. If we consider here n is known and p is unknown, and if we write a statement like p is equal to 0.7, then the probability distribution is completely specified. Whereas, if we write p is greater than 0.6, then the probability distribution is not completely specified. It only says p is some value greater than 0.6. So, this gives a simple hypothesis. In a simple hypothesis, completely specifies the given probability distribution. Otherwise, it is called composite hypothesis. So, you can see here that the testing of hypothesis problem can be classified as the problem to test a simple hypothesis or to test a composite hypothesis. See, we may have a situation like this. Suppose we are considering normal distribution with parameter mu and sigma square. We want to test whether sigma square is equal to 1. Now, if I say sigma square is equal to 1, this is not actually a simple hypothesis, because this is only specifying the value of sigma square, mu is not specified here. So, this is actually a composite hypothesis. Usually a notation h or h naught etc. is used to denote a hypothesis statement. For example, here we may write H naught, here we may write H 1, here we may write say H 2, here we may write say H 3, etc. So, a hypothesis usually we use a notation H for denoting the hypothesis. Now, there is another classification of the nature of the hypothesis. We say something is a null hypothesis and there is an alternative hypothesis. Now, what is a null hypothesis? We framed this problem here that we want to test whether the new medicine is more effective than the previously used medicine. So, we have framed a hypothesis whether p is greater than 0.6 and then we say whether it is more effective or not. So, or not statement that is corresponding to p is less than or equal to 0.6. We may also say here we may put greater than or equal to and here we may put less, of course, it does not matter here. Or we might have put one hypothesis as p is equal to 0.7 or p is equal to 0.5. So, we may call this as H naught and this as H 1. Now, one initial hypothesis which we want to check, that is certain original assumption about the parameter of the population, that we call or we term it as a null hypothesis. Now, when the null hypothesis is not likely to be true, in that case something else is going to be true, that we designate as an alternative hypothesis. So, we may have something like we are considering certain, we are measuring certain thing. Now, that measuring device may introduce errors in the measurement and then we want to check whether the average errors are eliminated or not. So, if my mu is the average error of measurement, then we may like to check whether this average is 0 or it is not 0. If it is 0, then we will say our measuring device performs consistently or it is performing well. Now, when we introduce the problem of testing of hypothesis, ultimately we have to check whether the hypothesis is consistent with our given data or not. When we test with respect to our given data, it is called the test of hypothesis, test of statistical hypothesis. So, a test of a hypothesis is a decision to accept or reject a hypothesis. So, for example, we take a sample x 1, x 2, x n. Based on that, we make a decision. Basically, what we will do? We will partition the entire sample space into two regions. When the value, our sample point belongs to one portion of the sample space, we will say accept one hypothesis. If it is in the other case, we will say accept the other hypothesis. Based on that, we frame what is called acceptance and rejection or critical regions. Let S be the space of x is equal to x 1, x 2, x n. We partition S into complementary regions, say A and R, that is A intersection R is phi and A union R is equal to S. Suppose we are considering the hypothesis testing problem H naught theta belonging to say omega naught and H 1 theta belonging to omega 1, where omega naught and omega 1 are subsets of the parameter space, and certainly omega naught intersection omega 1 must be equal to phi, they must be disjoint. If say x belongs to R, we reject H naught. So, R is called the rejection region or critical region. If x belongs to S, we accept H 1 or we say do not reject H naught. This is called the this is A, this is called the acceptance region. So, we actually I have written wrongly, we accept H naught. When x belongs to A, we accept H naught or we say do not reject H naught. Here I would like to mention one point. The decision to accept or reject a hypothesis is based on the sample. So, when we observe a sample based on which if we can say our null hypothesis is not consistent with the value of the test statistic or value of the criteria that we are deciding, then we simply say that the H naught or the null hypothesis is rejected. However, when our hypothesis turns out to be consistent with the criteria for the test criteria, in that case we do not use the word that we accept H naught, we rather say that there is no sufficient evidence to reject H naught. So, roughly speaking we say that H naught is accepted, but we do not say it that way. This is something like what we say in a testing of hypothesis problem. Let me introduce the one problem. Let us consider that same where our x 1, x 2, x n are error measurements, and we are assuming that they follow say normal mu 1 distribution. Here I am assuming that sigma square is equal to 1. We want to test whether mu is equal to say minus 1 against mu is equal to plus 1. It is something like saying that whether the scales are negatively weighing or they are weighing positively. Let us consider here we can consider x bar follows normal mu 1 by n. We can make a decision based on x bar. So, we give the acceptance region as x bar less than or equal to 0 and the rejection region as x bar greater than 0. Naturally, our decision is based on sample and therefore, there is a chance of errors. There are two types of errors that are committed. One is called type 1 error, that is rejecting H naught when it is false, when it is true, and type 2 error accepting H naught when it is false. So, this is called the error of the first kind, and this is called the error of the second kind. Usually we use a notation alpha is equal to the probability of type 1 error and beta as probability of the type 2 error. Let me calculate these probabilities for this example. For the above example, alpha, that is the probability of type 1 error, that is probability of rejecting H naught when it is true. Now, when are we rejecting? We are rejecting when x bar is greater than 0. So, probability of x bar is greater than 0 when it is true. True means mu is equal to minus 1. Now, when mu is equal to minus 1, x bar follows normal minus 1 by n. So, this value then you can write as probability of x bar plus 1 into root n greater than 1 root n here. So, this will have root n x bar plus 1, this will follow normal 0 1. So, this value turns out to be probability of z greater than root n. Suppose n is equal to 9 here, then this value will turn out to be probability of z greater than 3, that is 0.0013 in the case of standard normal distribution. So, the probability of type 1 error is 0.0013 here. Let us consider say beta here, that is the probability of type 2 error, that is probability of accepting H naught when it is false, that is equal to probability of x bar less than or equal to 0 when it is false, that is mu is equal to 1. So, now when mu is equal to 1, x bar follows normal 1 by n, that means x bar minus 1 into root n will follow normal 0 1. So, this is probability of root n x bar minus 1 less than or equal to minus root n, that is equal to probability of z less than or equal to minus root n. Now, in this particular case, when I have taken n to be 9, this is again 0.0013. So, in this case, both probability of type 1 error and probability of type 2 error, they are 0.0013 here. So, what is a test of statistical hypothesis? A test of statistical hypothesis divides the sample space into two regions, that is the acceptance region and the rejection region. So, based on this, what we are doing? We are actually determining a function say phi x, this is called a test function, this we can call probability of rejecting h naught. So, we are actually assigning a function here and we are calculating expected value of phi x, that is equal to probability of rejecting h naught when theta is the parameter value. Now, remember here, when theta is belonging to the null hypothesis space, then this is becoming the probability of type 1 error, and when theta belongs to the alternative hypothesis set, then this is becoming 1 minus the probability of type 2 error. So, we give it a new name, we call it beta star of theta. This is called the power function of the test. So, phi here. So, when theta belongs to omega 1, then beta star phi theta is actually 1 minus beta phi theta. This is called the power of the test. Now, you can notice here that the probabilities alpha and beta that have been calculated, they are based on the complementary regions. Here x bar is greater than 0 and x bar is less than or equal to 0. So, they are based on the complementary regions. In an ideal test, both alpha and beta must be equal to 0, but this simultaneous minimization is not possible. If we decrease alpha, say, then beta will increase. If we increase alpha, then beta will decrease. Therefore, as a compromise solution, what we do, we fix one of the errors and then we try to minimize the other one. This gives us the concept of the most powerful test. So, what we do, we fix, let us call alpha theta, that is equal to probability of type 1 error, that is when x bar belongs to the rejection region, that is probability of rejecting h naught when theta belongs to the null hypothesis set. So, consider the maximum value of this, let us call it alpha star. This is called the size of the test. So, what we do, that we consider for a fixed alpha star that value, that test phi which minimizes beta star theta. So, when omega naught, see this beta star theta is actually probability of rejecting h naught when it is false, when theta belongs to omega 1 here. So, this is called the power of the test. So, when alternative hypothesis is simple, then the test which minimizes beta star is called the most powerful test or MP test. Otherwise, when alternative hypothesis is composite, then the test that minimizes beta star for theta belonging to omega 1 is called the uniformly most powerful test. That is, we call UMP test. So, in a given problem, our aim is to find out the most powerful test or the uniformly most powerful test. This problem of finding out the most powerful test has been solved by statisticians, and a solution which is given for the simple versus simple case was introduced in 1920s by George Neyman and E.S. Pearson, and the result is famously called Neyman-Pearson fundamental lemma. This result, which was introduced for testing simple versus simple case, was later on extended to the case of composite hypothesis also, and the solutions for the cases where the uniformly most powerful tests or the uniformly most powerful test within a certain class of tests were also derived. In this particular lecture, I will be only giving the Neyman-Pearson fundamental lemma, and then based on this how various tests have been derived. So, we will give the form of the tests for testing the parameters of the normal population only, and we will not discuss the general methodology for finding out the test. There are other methodologies also, such as the likelihood ratio test, etc. However, we will not be concentrating on those things in this particular lecture here. Let me introduce the main part of the Neyman-Pearson lemma. So, let us consider, say, hypothesis H naught, say f x is equal to f naught x against H 1 f x is equal to f 1 x. Of course, this means that the density, whether the density is f naught or the density is f 1. So, this is the testing problem. Then the Neyman-Pearson lemma says that the most powerful test at level alpha is given by phi x is equal to 1, rather we can say reject H naught if P 1 x is f 1 x is greater than k times f naught x, accept H naught if f 1 x is less than k times f naught x. Where k is determined by the size condition, size alpha condition. Let me solve one problem. Let us consider the normal example x 1, x 2, x n following normal mu 1, and our hypothesis testing problem is whether mu is equal to minus 1 against whether mu is equal to plus 1. Let us write down the density function here. F x is equal to 1 by root 2 pi to the power n e to the power minus 1 by 2 sigma x I minus mu square I is equal to 1 to n. So, if we consider f 1 x by f naught x, that is equal to e to the power half sigma x I plus 1 square minus half sigma x I minus f 1 is corresponding to mu is equal to 1. So, this will be with the minus here and this will be with the plus sign here. So, we are saying it is greater than k. Now, we can simplify this. If we take the logarithm here, this will imply sigma x I minus 1 square minus sigma x I plus 1 square greater than some constant, say k 1. Now, this can be further simplified. We can write it as minus twice sigma x I plus twice again minus twice sigma x I greater than some k 2, or we can say sigma x I is less than k 3. Let us check the steps here. F x is equal to 1 by root 2 pi to the power n e to the power minus 1 by 2 sigma x I minus mu square. So, if we write f 1 x here, f 1 will become equal to 1 by root 2 pi to the power n e to the power minus 1 by 2 sigma x I minus 1 square, and f naught will become equal to 1 by root 2 pi to the power n e to the power minus 1 by 2 sigma x I plus 1 square. So, if we consider f 1 by f naught here, then this will become plus here and this will become minus here, this is plus, this is minus here. So, here we will get plus and this will become plus. So, this is greater than k 3, where k 3 is determined by the size condition. So, here we make use of the fact that probability of, so we can write it as x bar greater than say k 4. So, x bar greater than k 4, this should be equal to alpha when mu is equal to minus 1, that is the probability of rejecting h naught. This is the rejection region. We are saying reject h naught if this statement is true. Now, again x bar follows normal minus 1 1 by n. So, we will get root n x bar minus plus 1 following normal 0 1. So, this statement can then be written as root n x bar plus 1 greater than k 4 plus 1 into root n, that is equal to alpha. So, this is nothing but z. So, we can write z is equal to root n x bar plus 1 greater than z alpha. So, the test is reject h naught if root n x bar plus 1 is greater than z alpha, else accept h naught. So, this is nothing but the most powerful test for testing h naught against h 1. Now, note here in the null hypothesis we are saying mu is equal to minus 1 and in the alternative hypothesis mu is equal to 1. So, actually roughly speaking we can say that in the alternative hypothesis the average value is higher than the value in the null hypothesis, and therefore, the rejection region also reflects that we are rejecting actually for higher value of x bar, because x bar is actually an estimator for mu here. It is actually a consistent and unbiased estimator, and here it turns out that x bar is greater, then we reject h naught. Likewise, in case of in place of here minus 1 and mu 1, if I had written here say mu naught and here I had written mu 1, where mu naught is less than mu 1, the form of the test statistic would have been the same, except for the fact that here 1 would have been replaced by x bar minus mu naught. So, in fact, this observation led to the solution of the composite hypothesis also. That means, in place of say mu is equal to mu naught against mu is equal to mu 1, if we consider say mu less than or equal to mu naught against mu greater than mu 1, etcetera, then the uniformly most powerful tests are found out, and let me introduce those testing problems here. Testing for parameters of a normal population. So, x 1, x 2, x n follows normal mu sigma square distribution here. We are considering say case 1 when say sigma square is known. We are considering say hypothesis say mu is less than or equal to mu naught against mu is greater than mu naught. Here the test is then reject h naught if root n x bar minus mu by sigma mu naught by sigma is greater than or equal to z alpha. The alternative region will become the acceptance region, accept h naught otherwise, or you can say that there is no region, not sufficient region to reject h naught. See, this case could have been that in the null hypothesis we have greater than or equal to this, and in the alternative hypothesis we have the. Then if we look at the curve here of the normal distribution, then this is z alpha, here you will have minus z alpha. So, if it is negative side, the smaller side, then the test will get reversed. You will say reject h naught if root n x bar minus mu naught by sigma is less than or equal to minus z alpha, and the other region is complementary region will be the acceptance region. Now, we may also have the case when the alternative hypothesis is on both the sides. For example, you may discuss mu is equal to mu naught or say mu is not equal to mu naught. In that case, on both the regions we will be considering rejection. So, if we consider the division of the alpha into two portion, then this will become alpha by 2 and minus alpha by 2 here and alpha by 2 here. So, we will then consider reject h naught if modulus of root n x bar minus mu naught by sigma is greater than or equal to z alpha by 2. Let us also consider the case when sigma square is unknown. When sigma square is unknown, here our decision making will be dependent upon square root n x bar minus mu naught by s, let us call it t. Then we will have the test statistic as reject h naught if t is greater than or equal to t alpha n minus 1. On the other hand, if we are considering say h naught mu is greater than or equal to mu naught against h 1 mu less than mu naught, in that case we will say reject h naught if t is less than or equal to minus t alpha n minus 1. However, if I have h naught mu is equal to mu naught against h 1 mu not equal to mu naught, then as in the normal distribution, t distribution is also symmetric distribution. So, you will have reject h naught if modulus of t greater than or equal to t alpha by 2 n minus let us also consider the test for sigma square, testing for sigma square here, and again we may have two cases. Mu is known. If mu is known, then we can consider sigma xi minus mu square, and we can consider this divided by sigma naught square. Let us call it say W1. Then this follows chi square on n degrees of freedom when sigma square is equal to sigma naught square. So, if we consider the hypothesis, say sigma square is less than or equal to sigma 1 square, sigma naught square against H1 sigma square greater than sigma naught square, then our rejection region will be, if we consider the chi square curve here, then on the larger side. So, chi square alpha n minus 1. So, here n, reject H naught if W1 is greater than or equal to chi square alpha on n degrees of freedom, accept H naught otherwise. Similarly, we can consider the complementary region, and here we will say reject H naught if W1 is less than or equal to chi square 1 minus alpha n. In the case of two sided region, suppose we are considering sigma square is equal to sigma naught square against sigma square is not equal to sigma 1 square, then reject H naught if W1 is less than or equal to chi square 1 minus alpha by 2 n, or W1 is greater than or equal to chi square alpha by 2 n. The life in years of a battery is normally distributed. A random sample of say 16 batteries produced a sample variance say sigma square is S square is equal to 3. We want to test the hypothesis sigma square is equal to 2 against say H1 sigma square is greater than 2 at alpha is equal to 0.05 level of significance. Here we apply the method here described, that we calculate W1, that is sigma. Here mu is not known here. So, we have to consider the procedure for mu unknown. Let me give the procedure for mu unknown. Case 2, mu is unknown. When mu is unknown, then we consider the quantity W2 is equal to n minus 1 S square by sigma square, that follows chi square n minus 1. So, when sigma square is equal to sigma naught square. So, the tests will be based on this, that is rejection regions and acceptance regions. So, using this we calculate 15 into 3 by 2, that is equal to 22.5, and the value of chi square on 15 degrees of freedom and 0.05 is equal to 24.9958. So, here we say that H naught sigma is equal to cannot be rejected, because here the general rejection region for H naught sigma square is equal to sigma naught square against H 1 sigma square is greater than sigma naught square. This rejection region would have been reject H naught if W 2 is greater than chi square alpha n minus 1. So, here we cannot reject the null hypothesis here. We also give a large sample test for variance. So, let x 1 x 2 x n be a random sample from a population with variance say sigma square. Then S is approximately normal sigma square by 2 n for n large. So, S minus sigma by root 2 n, this is approximately normal 0 1 as n tends to infinity. So, we can consider here the test based on root 2 n S minus sigma naught by sigma naught as, let me call it Z. Then if I consider the hypothesis as sigma square is equal to sigma naught square against sigma square not equal to sigma naught square, then we can consider reject H naught if modulus Z is greater than or equal to Z alpha by 2 here. Let me consider one example for this problem. Let a sample of size n is equal to 10 give S is equal to 6.9. We want to test the hypothesis whether sigma is less than or equal to 7 or sigma is greater than 7. So, Z is equal to root 20 6.9 minus 7 by 7, that is minus 0.0639. If we consider say alpha is equal to say 0.05, then Z of 0.025 is equal to 1. Z is equal to 0.05, that is equal to 1.645. So, we cannot reject H naught. If we consider say reverse of this, say H naught sigma greater than or equal to 7 against H 1 sigma less than 7. In that case again H naught cannot be rejected. So, if we consider H naught sigma is equal to 7 against H 1 sigma is not equal to 7, here you will consider two sided alpha by 2. So, Z alpha by 2 will be equal to 1.96. So, again H naught is not rejected. So, actually we can say that sigma is approximately 7 here. Let me give one or two more examples here. suppose we have x following Poisson lambda distribution. We want to test whether lambda is equal to 2 against lambda is equal to 1, and we have a random sample x 1, x 2, x n from this population. So, we consider here the density function f x lambda, that is equal to e to the power minus n lambda, lambda to the power sigma x I by product x I factorial. So, if we consider f 1 by f naught, and that is equal to e to the power minus n by product x I factorial divided by e to the power minus 2 n 2 to the power sigma x I divided by product of x I factorial. Now, this term cancels out, you are left with e to the power n and divided by 2 to the power sigma x I. So, rejection region is if e to the power n divided by 2 to the power sigma x I is greater than or equal to k. So, here you can write it as n minus sigma x I log 2 greater than or equal to log k, let me write it as k 1, or sigma x I is less than or equal to some k 2. Once again here you notice that in the alternative hypothesis the value of lambda is smaller than the value in the null hypothesis, and therefore, the rejection region is for the lower value. Here you notice here that sigma x I follows Poisson n lambda, that is 2 n when h naught is true. So, probability of sigma x I less than or equal to k 2 when lambda is equal to 2, that is equal to alpha. That means, k 2 is the Poisson 2 n point, that is the point on the Poisson 2 n distribution, that is the probability up to this is equal to alpha, up to this the probability is summed up to alpha here. So, this will be the most powerful test of size alpha here. Now, here you may notice, since Poisson is a discrete distribution, there may be a case that up to a certain point the value alpha will be achieved, and after that the value will exceed alpha. So, that means, at one point the value will be below alpha and after that the value will be above alpha. So, at that point we do the randomization and we allocate that point with certain probability, say gamma, where you reject and 1 minus gamma you accept. You choose the gamma in such a way that the total actually becomes equal to alpha here. In the next lecture, I will consider the 2 sample problems for the normal distributions, and we will consider testing about the equality of means, the equality of variances, etc., and we will consider certain examples based on that. That will be the part of the next lecture.